Okay, today we're going to do a little intro into L'Hopital's rule. We're going to do an example, we're going to kind of explain the concept, and we're going to write down the definition. So, first of all, let's think our way into this. Say that you have the limit. I'll do it down here so we can write the definition above. Say that you are looking for the limit of x approaches anything, infinity, 0 from the right, 4, it doesn't matter, of a function of x over another function of x. So a rational function, right? Say that you have that, and when you substitute, for example, say you have infinity. Say you substitute infinity, and you end up with infinity over infinity. Well, then what do you do, right? I mean, or you end up with 0 over 0. Like, that's not an answer to that's not an answer. That's not a valid answer anyways. It's an answer, but it's not what anybody wants to see as the solution of your problem. No math professor wants that. So what do? Well, you can divide by the highest power of x. You can divide the numerator and the denominator by the highest power of x. That's legitimate and it always works. But it's also kind of a lot of work. It could be easier, and it could be easier with L'Hopital's rule, which states that, let me get rid of that infinity, which states that if the limit follows any of these indeterminate forms, these are indeterminate forms, okay? Let me write it down. Indeterminate forms. And what that means is that you cannot determine what they are, right? That then the limit of x approaching a of this function over this other function is the same as the limit of x approaching a of the derivative of the function in the numerator over the derivative of the function in the denominator. Well, let's think about this some more. It has to be a fraction. The rule, as you can see in this rule, it's going to have to be a fraction, right? If you're going to use L'Hopital's rule, you've got to use it on a limit of a fraction. Well, let's think about that for a second, because 0 times infinity is not a fraction. Rewrite it though, because infinity can be a lot of things, but one thing infinity can be is 1 over 0, right? So it's 0 times 1 over 0, which is 0 over 0, and there you have a fraction, and you can use L'Hopital's rule on that. So you're going to have to be kind of clever about how to write down your function. Okay, so we have the rule, and let's write down the corresponding sentence. It's always good to have it in your head. If the limit is in any of these indeterminate forms, right? Of these indeterminate forms. Rewrite the limit. The limit. Like this. Okay, we have the rule. What does that mean for like a function where when you take the derivative of the top and the bottom, you still end up with infinity over infinity or 0 over 0, right? I mean, then what? You just use L'Hopital's rule again. It's the same as limit of x approaching a of f double prime of x over g double prime of x as well. And that goes on forever. I mean, you can do it until it's a constant and then the derivative of it is 0. I mean, you don't want that. You'll probably end up with 0 over 0 again, but you can apply it. When you apply it, note that you need to write over the equal sign a little L apostrophe H for L'Hopital. So people know that you have applied L'Hopital's rule. You're not just randomly like doing something they don't understand, right? Document what you're doing. That's the one important thing. The other important thing is to understand why we need a special rule for these indeterminate forms and what makes them indeterminate. I mean, I guess that's the same thing. Why is it that 0 times infinity is indeterminate? Well, I guess infinity is always indeterminate, right? Because it's literally the opposite of finite. It's infinite. It's infinite, right? Well, For example, with infinity minus infinity, we don't know what infinity is, but we know that this infinity could be larger than that infinity, or it could be smaller. You don't know, right? If this infinity is larger than this infinity, then this is probably still going to be infinity because you're subtracting a smaller number from a bigger number. But if this is smaller, then you're going to go over into negatives, right? So you don't know what your answer is going to be. If you have 1 to the infinity, like what is that going to become? You don't know. If you have 0 to the 0, say you have two quantities here, and one of them is approaching 0, and the base is approaching 0, right? The exponent and the base are approaching 0. But what if they're approaching 0 at different rates? And this one becomes 0 before the base becomes 0. Well, if the exponent becomes 0 before the base becomes 0, then you have a number to the 0, which is going to be 1. But if the base becomes 0 before the exponent becomes 0, you're going to have 0 to the essentially 1, and that's going to be 0 because anything to the 1 is itself. So you see the problem is that we just don't know. If we don't apply L'Hopital's rule or the rule of dividing by the highest power, then we just don't really have a solution when we have something like this, right? We don't have a real limit. Like conceptually, yes, if it's infinity over infinity, I mean, that's mathematically correct, but it doesn't tell us anything, right? So let's do an example. Let's do an example over here to see if we understand what we're doing. And let's use limit of x approaching infinity because those are pretty common on these questions if you're doing them like either out of a Calculus 1 book, for example. Did I mention this is probably Calculus 1 level? Say that you have the limit of x approaching infinity as x approaches infinity of 3x squared plus 2x plus 1 over x squared minus 3x minus 1. Well, let's think about this in the way that we know first. The highest power in this rational function is x squared. We could just divide every term on top and bottom by x squared, and we're going to end up with 3, right? But we don't need to go to all that trouble. We can make it easier. If it's not that much trouble, maybe you want to do that instead, but you probably want to understand this, right? Well, if we apply L'Hopital's rule, and when we say that we're applying L'Hopital's rule, right? We can make this the limit as x approaches infinity of the derivative of this, which is f of x. In this particular case, we're calling it f of x, over the derivative of g of x, which is the denominator. Well, that's going to become, in this case, that's going to become 3 times 2x to the 1 plus 2 over 2x to the 1 minus 3. I don't need to write that out. That's the same as saying 6x plus 2 over 2x minus 3. And now let's not forget that there's a limit there, right? Let's just write it there. It's good never to forget it as x approaches infinity. Okay, well, that's the same thing. Now you know how we got there. You probably know how to derive things, really, but remind yourself. So now what do? We put in infinity again, right? Did I mention that actually? The reason that we can apply this is because when you replace x by infinity here, you end up with infinity over infinity. I'm not sure I mentioned that. Sometimes you get further along and you just take these things for granted, but this is not the business for that. So you get infinity over infinity. That's why we're applying L'Hopital's rule. Well, here we're still going to get infinity over infinity, right? This is still infinity over infinity if we substitute in infinity for x. So we need to apply it again. So we're going to write it again. And it's going to equal limit as x approaches infinity, because we haven't taken the limit yet, right? So we still have the limit of 2 times, I was looking at the 2. 2 times 3 over 2, which is 6 over 2, which is 3. You don't even have to substitute because the limit of a constant is the constant. But that's one of the limit rules. So as you see, now it was really easy to get to that. I mean, we could have divided everything by x squared, but we didn't need to. I mean, that was so easy, right? You apply it twice, and there you have it. And that's kind of a good example. Now, don't make the mistake that I made where you're just kind of like, oh, I can apply L'Hopital's rule because this is under the L'Hopital's rule, like problems section, because you need to know what indeterminate form you're trying to solve for, actually. So learn from my mistake. Check what it is you're dealing with. Because this was infinity over infinity, but it also could have ended up being like 0 over 0, or it could have ended up being, infinity minus infinity, in which case you'd have to rewrite it before you could apply L'Hopital's rule. So before you do anything, you get a L'Hopital's rule problem. Before you do anything, check what indeterminate form it corresponds to. And if it's not like in the L'Hopital rules section of your book, if you've moved on and you're applying it where it needs to be, it's extra important because maybe you can't even apply L'Hopital's rule. Maybe it comes out to something that isn't in this list of indeterminate forms, or maybe something else would just be much easier. So the first thing you need to do always is check the indeterminate form it corresponds to. Then, if you can apply it, either rearrange it or just apply it immediately, depending. Write down that you're applying it, do it. Does it still come out to an indeterminate form? Check again which one. Maybe it'll come out to a new kind of indeterminate form. And then apply it again until you come to a solution. There are certain types of problems. Probably aren't a lot of them. I came across one lately where you apply L'Hopital's rule. I think it's like hyperbolic sine over hyperbolic cosine. And you apply L'Hopital's rule, and it becomes hyperbolic cosine over hyperbolic sine. And then when you apply it again, it becomes the original function, like perpetually. It will never be anything but hyperbolic sine over hyperbolic cosine, or hyperbolic cosine over hyperbolic sine. You can't apply L'Hopital's rule, right? It's just because e to the x is always e to the x when you derive it. And if you have a negative in the top, it just keeps switching. It just keeps switching to the same things again and again. So just sit down and remember, this only applies to certain things. And anyway, this is our solution to our example. There's a lot of other problems. I'm probably going to do a couple of them. Remember that you can do this perpetually, pretty much. I mean, not really, because it does end at a certain point when it becomes a constant. But if your exponent was 99, you could do it 99 times. That sounds really boring, but you could. So yeah, I hope this helped you. And if I left something out, maybe I'll do another video, or maybe I'll do some examples. If I do, then I'll link them.